we were left off looking at this GCD algorithm, and I basically said we could kind of pencil and paper and understand why this approach works for calculating the GCD of two integers. But in terms of implementing it, where our goal was to just have another example of what a recursive solution could look like, we can kind of just take it for granted that this is, this is the algorithm, this is the approach that we can take. And again, the two things we tend to have in our recursive function, our way of solving a problem via recursive algorithm or recursive implementation, a recursive solution, is we have to have some sort of base case. You can think of that as also like the terminating condition. So it's not that different in some high-level concept from our while loop, right? Our while loop goes forever until there's some reason it's going to stop. If the recursive function, it's kind of the same thing. We are going to keep recursively calling the same function until we reach some reason to stop doing so. And that's our base case. That was the Matryoshka dolls, and that's getting to the very tiniest one at the end that doesn't open up any farther no matter how hard you try. In this case, we do have kind of explicitly listed the base case for GCD. And in terms of implementing it, that'd probably be the first thing that you want to implement. Usually, if you've hit the base case, get out of there. Return 0, or return A in this case. You are done. Don't go any further in the function. And then all we have, which is just very slightly different than the Fibonacci example, is just two potentially separate recursive cases. If A is less than B, do GCD of BA. Otherwise, do GCD of A minus B, comma B. And ultimately, we can kind of just implement this almost line for line exactly in our C code. So let's give that a try. So we need to have a function called GCD. What type should it return? A what now? Integer would be great. And let's just use A and B, because that's what was described there. Call it input 1, call it input 2. We have our base case. Well, first off, we've liked to have our like debugging statements, right? Which is, as you're having a function that calls itself potentially over and over again, it can be very helpful just to say, here's where I currently am. And that's why when I say inside, that's all I mean, right? When we get to this line of code, that means we are currently inside this function, and those are the current values of A and B. And you don't need that. That's just for debugging purposes. And so I think we'll continue to do that for our examples. We have our base case. If B is equal to 0, the result is A. In terms of what that looks like in C, the only difference is, we have equal corresponding to the equality operator. Otherwise, it's exactly the same. If B is equal to 0, the GCD of A and 0 is always A. How do we implement that? That's it. I'm not even going to add a new line because it's just so nice and tight and just fits so nicely on just one line there. And we can put braces and things like that, but it's just a one-line if statement, right? If B equals 0, return A. If A is less than B, so we know it's at least that much, what should we return? That's it. I'm not going to add a new line there either. And then otherwise, else, we could write an else statement. Otherwise, we don't really need to, because if we've gotten to that point, we've reached the else block, right? Everything else is returned. So we got our 3-line plus an unnecessary debug statement implementation of GCD. We should probably then, declare a few test cases. This is where that test tab would be useful, but that's not how we've been doing things all semester. It was 4 and 8 was the first example. So we'll say the GCD of, we'll actually print out the values. The GCD of A and B is whatever we get for calling GCD of A and B. Then the other example was 15 and 25. We should get that result. 16 and 35 is the third example. And we can just create a random example as well. That's fine. Where A is then rand and B is, that's fine, we can do that. GCD of some random value and some random value is probably going to be 1. I'm not a mathematician, but I think it's unlikely you have common factors of 2 randomly generated 32-bit integers. But we'll see. We can run it a bunch of times until we get a non-1 value. There's a lot printing out there, but we can see what we happen. So we first called it with, let's call it from the shell so we can actually scroll all the way back here. We pass 4 and 8. So notice that this printf hasn't triggered yet, even though it's the first printf that's encountered in our function, but that printf only is going to print something out when it has the values it needs to print out. So because in doing so, we have another function that's being called first. The very first thing that prints out is that inside GCD of 4, 8. First time through, A is less than B, so we instead now recursively call GCD with 8, 4. A is now greater than or equal to B, so we then call GCD of A minus B, which is 4, so 4, 4. We have to then do that again. We call GCD with 4, 0. We get B equals 0. We get GCD of 4, 0 is equal to 4. And then recursively, all those functions return back up to return that value of 4 all the way back up the stack. It's a little different than the Fibonacci example in that in the Fibonacci example, we were taking the recursive call and then doing something with that result. So there's still a little bit more logic required in the function, but otherwise it's exactly the same. We call that function at some assumed depth here to get to a result in which B is equal to 0. And however many iterations that takes is going to, in this case, be a function of how big A and B are for your code. And then you just return that value all the way back up. So this function returns 4, which then causes this function to return 4, which causes this function to return 4, causes this function, which finally causes that final function to return 4 back to our printf and back out to main. And the result is correct. Same as for 15 and 25. 16 and 35, you can see what kind of happens. They're never, ever equal to anything other than 1 and 0 in the end. And for our two kind of random numbers that are generated there, well, first off, they're quite a bit larger, but it's doing the same exact thing. It's figuring out which of the two is larger, swapping them if need be. Otherwise, it's subtracting the smaller from the larger of the two until you finally get one of the values being equal to 0. And in this case, they are both even, and that's a good point. So there's probably a 50-50 chance. That's not 50-50. You get a 1 in 4 chance that both numbers would be even, right? And so at least you get a GCD of 2 back out for 2 arbitrary values. But I think the way large numbers works, it's unlikely to get a GCD. There you go. Got 66 is our GCD of those 2 arbitrary numbers here. Questions about this example before we jump into a admittedly somewhat more complicated, but hopefully slightly more meaningful example as well. Okay. Well, even just 2 relatively prime numbers is what we're getting when the result is 1. Any 2 prime numbers would also have the same instance, right? If we try 3 and 11, we would get 3 and 8, 3 and 5, 2 and 3, and then 1 and 2, 0 and 1. Okay, let's talk about finding palindromes. As part of our problem-solving toolkit, of which we're just going to add this to our list, we tend to have a good fit for a recursive solution if it is a problem that can be broken down into subproblems. That's a tough thing to say, definitively. It's easy to see it after the fact, and I think that's true of a lot of different algorithmic approaches and ways of thinking about breaking down problems. But that is the approach that you want to consider. Well, would a recursive solution make sense for this big problem? The answer is yes, if there's a logical way and a relatively straightforward way you can take that big problem and break it down into a smaller problem. There's still all the implementation details, even if you come to that determination, but that's part of the thought process that can just add to your tool bag of tricks of things that work for you. This sample problem is detecting whether a given input string is a palindrome or not. And for those who aren't super familiar, palindrome is a sentence, a word, a phrase, just a series of text or even numbers that reads the same backwards as forwards. And to make this a slightly more realistic scenario, we can maybe assume that for this function, we could ignore case and punctuation. So radar is a good example, right? R-A-D-A-R going forward, R-A-D-A-R going backwards. There are all sorts of very clever palindrome sentences that people much smarter than me have come up with over time. Never odd or even is one that I happen to like, because you have to take my word for it, I guess. If you read it from right to left, character by character, sometimes you have to change the punctuation, sometimes you have to change the capitalization, sometimes you have to kind of ignore or change the punctuation here, but spacing as well. you get the same exact characters reading from right to left as you have from left to right. And as I mentioned on Monday, it is generally the case, although I think on Friday we'll come up with a scenario in which that's not strictly true, but it is generally the case that you never need to absolutely have a recursive solution for something. So here, I think this is one in which we can come up with a recursive solution that is going to be relatively elegant and a lot cleaner than the iterative solution where you might have to have like 2 while loops, one going from the front and one from the back and doing that. We could probably sort it out if we had to. If I said you had to write an iterative solution for this, I think you could also figure it out. But it is oftentimes the case, or there are certain key circumstances where it's the case, where the recursive solution is just going to be a lot more straightforward to both think about and actually implement. Here's my favorite palindrome video. I don't know if it'll play, and I also don't know if my video will get struck if I attempt to record this with my YouTube video for this class. And he's just going through, it's a Bob Dylan spoof, but just going through various complicated palindromes over time. I've always wanted to be that cool professor who plays YouTube videos before class, but cool is a bit of a stretch for me, so we'll go with Weird Al and relevant videos relevant to the topic at hand. All right. You seem enthralled. You can watch that later. The song is called Bob, and it's all just a series of pretty wacky palindromes. I don't think he came up with any of them either, but they're just well known. And it's given me some really good suggestions after that. Okay, so how do we actually implement this? I said, in terms of thinking recursively, the question we have to conceptually answer in our heads is, can we take the big problem of entire sentence, is it a palindrome or not, and break it down into recursively smaller subproblems. So to get there, you have to say, from big problem to slightly smaller problem, what would that step require? Usually it requires some method of taking a quote-unquote larger input and simplifying it to become a smaller input. For like the Fibonacci and GCD, that literally meant larger integer to smaller integer. I mean, so can we go from the really large input value A to now a smaller input value A the next time down? Same with Fibonacci. To calculate Fibonacci of n, we then calculate Fibonacci of n minus 1. So in that case, it literally meant larger value to smaller value. Here we're not dealing with numeric values, but string values. So generally we'd be thinking of, can we take a input that is a large string and solve the problem of a smaller string to get the same result? And there's different ways we could do that. We could recursively just pop off the first character or the last character, or maybe split it into a left half string and a right hand string, or maybe figure out what the middle character is and remove that middle character. There's different approaches we could take. The most promising, or I think the most elegant looking solution for this problem is to consider that if never odd or even is a palindrome, then so is ever odd or eve. And that's just another one that just fits in terms of English, right? By taking off, removing the first character and the last character, if the big problem string was a palindrome, then the substring we've created is also going to be a palindrome, and really all the way down. If I then take this string and remove the first character, I'm still going to have a palindrome. And so that leads us to, I'm not going to say an easy recursive solution, but that's just one way we can break down this palindrome problem. If we have the first and last character, they have to be the same. And then if recursively, as we pop off, remove the first, remove the last character, and that is also a palindrome, so that's going to be the recursive case here, then what we had as an input is also going to be a palindrome. There's a couple base cases that really depends on the string that we have to watch out for. If there's 2 characters, then that's not necessarily a base case because we have to check if they match. If there's just a single character remaining, which is going to happen if there was an odd number of characters in the original string, then I think we're okay. The letter A is itself, I guess, a palindrome, right? It's one letter and it reads the same forwards and backwards. So if you get down to a final level, a letter in your base case, you're okay. And I think also if you wind up with an empty string, then you're also okay. You've successfully removed first and last, first and last, first and last, first and last, and then the end result is something that is empty, then you've gotten that far, meaning that you have ultimately a palindrome string. So let's give this a try with this function. let's do it together versus kind of breaking this down into individual groups. But I need your contribution to make this work. So we have a function that's going to take our string as an input. And I think to make our code a little bit easier to use, we'll actually pass length information as well. And should return a 1 if it's a palindrome, and 0 if it's not a palindrome. So we pass in a few sample strings. You can manually determine whether or not these are palindromes or not, but we're going to write code to do that for us. As always, you want to try some clearly false values here to like confirm that your code actually works as expected. And we're just going to return the result and print out the result as to whether or not we actually have a palindrome here. So that's what we have in this example 1003 of our so-called palindrome. I've gotten us started, which helps. This is a good starting point. Our 3 sample strings, and then basically the template for that function to calculate if something is a palindrome. And then we're just calling it 3 times to determine for those 3 strings, is it a palindrome or not? It's nice to start with a place where your code compiles, right? And for your projects, I've always been recommending that, right? You start with hello world, which compiles. You probably never want to step away from your project at a place where it's not compiling. It may not be doing what you want it to do, right? But it can be pretty frustrating to come back 6 hours later, a day later, to a project that's no longer compiling because you may have lost a little context there. So starting with a place that compiles, staying at milestones where things are compiled and presumably executing as well is a better place to be than not to be in that spot. So that's what we have here. It doesn't do anything yet, right? It always returns 0. So when I print out palindrome status for those 3 strings, it says 0 because it's not actually calculating anything here. So what have we been adding to our recursive function calls for these other examples? If statements or print statements? Well, we've been adding if statements. Let's go back to this example that talks about our possible base cases. So we can absolutely do our base cases first, right? Do we have to go recursively, or are we done recursing? I would argue it could be implemented a couple different ways, so there isn't one correct way. We could make all 3 of these base cases, but certainly this one and this one I think can be base cases. So if we have an empty string, we have a palindrome, or if we have a string where it's just 1 character, then we have a palindrome. How would we implement that? If we have an empty string, it is a palindrome. We can go back to our GCD example as well, right? If we have an empty string, it's a palindrome. Or if we have a string of length 1, it is a palindrome. We're providing, and to make this code a little bit less painful to write, I'm just including length as an input to it as well. Absolutely, that's our base case. You could have written 2 base cases. If length equals 0, return 1. If length equals 1, return 1. Length, unless we do something pretty wacky, should never return negative. But what have we been adding to all of our recursive functions to help us debug? Yeah, thank you. We should do that, right? We're inside is palindrome, and we like to provide the inputs as well, right? So depending on how we implement this, we may want to actually explicitly specify we're going to print out a string of a specified length, not just an arbitrary string, and then %d for the actual length itself. So we're going to print out a string of that length, the actual sentence. You'd be surprised. So when we do point, we've done this before, right? Where it's like, for integers, we've done like 2.5d, or that wouldn't work for integers, but for floats, we've said, give me a float with 2 integer digits and 5 fractional digits. We can do the same thing for our strings as well. We can specify, I want a string that's no larger than 5 characters. I can also specify, I want a string, it does seem a little unhappy, but we'll see. It does seem quite unhappy because it's dot star, there we go, that's the syntax. Provide me a string of an arbitrary length that I then specify as my first argument before the string. So print out a string of exactly that many bytes, print out the actual string, and then print out what that value is for that. We can do this. It's not going to do much, right? It's just going to print out the inside palindrome. Okay, well, printed it out again, and 119 characters for the one, 33 for the other, and 41 for the third example. It's getting a little hard to just kind of see that printout. Like the word wrapping is making it more annoying than it would be otherwise. place. But all right, gets the job done. So there's our debug statement. We have our base case, which is if our length is equal to 0, we're good. If our length is equal to 1, is good. And then now we have to implement our recursive case as well. If the first and last characters match, and if the word obtained by removing the first and last character is a palindrome, then the initial word is a palindrome. It's a little bit harder than that, or there's a little bit more to it than that, because we do have things in our test inputs like capital letters and punctuation and things like that. We also do have functions that let us quickly determine whether we have something that is punctuation or not. What kind of function can we use to check? For a given value, is it text or is it something else? Is alpha, absolutely. And that's one of those things, there's that documentation for that C-type header, and there's a lot of those is functions, and it's okay to have to keep looking it up and remember exactly which one. You could also do is punct or is space and kind of check all those things. But we can check, right? You know, hey, is the first character even a letter? If not, you know, move on. Skip it. How would we do that? If it isn't a letter. So is alpha will return if it is a letter. Okay, so but is alpha, what do we pass as input? The first character, which would be what? Sentence of 0. And I think we want to check if that's return 0, because if it's not a letter, you can get stuck with double negatives with your code, and that's okay. Just, you know, when it's wrong, that's usually why you check the exact inverse condition you actually wanted to. Is alpha will return 1 if it is a letter. If it's not a letter, we don't really need to do this at all. We can actually say, hey, skip it. We have a function that says, you know, is palindrome. This can be recursive. We can do this recursively. Not sentence itself, but the next thing. The string starting 1 byte over, and it's going to have a length 1 less than what we currently have. That's one way to do it. There's not, you know, not just one way to do it. We can do the same thing for the last character. Well, I guess so, because, you know, we could update and modify the string itself. All I'm saying is, hey, call recursively the same function, assuming none of these, at least to begin with, will do that. Assuming we started with an exclamation point in our string. We check it's not equal to alpha, so it's punctuation or something. Call is palindrome again, and do plus plus sentence. It's a pointer. Move on to the next character. Increment the pointer by 1 element. Call that function starting on the next character in line. Actually, for the last character being a letter, it's even a little bit easier, right? Is the last character even a letter, how do we do that? Somebody else. Sentence of what? That's correct. That doesn't seem correct. Length minus 1. Now, we're removing the last thing from the string, not the first thing from the string, so the pointer can be the same. Just look at one fewer thing. That we could probably test. All these things end in punctuation. So for those tests, we should at least see that case triggering. Still not going to give us a result yet. Inside the palindrome with the entire string that ends with a period, then it calls it again, and we see what it prints out with that funky way of printing out strings, where it prints out the string of length 118 now, and it's basically stripped. It's still there, but we're just not printing out that final character, and we're not considering it part of the string anymore, just a random byte at the end of our string. It's the same string now without that period there. So that part kind of works. So if we get this far, and with our recursive call, you always should be kind of thinking in those terms, right? We have our base cases. So the else's are kind of assumed, right? It's like when you have a loop and you have a break, everything else after the break statement is kind of an else, kind of inherent else with the rest of your code. We got past line 11 because the length was greater than 1. We got past line 14 because the first character was alphabetic. We got past line 16 because the last character was alphabetic. So while the else's aren't so explicitly written, because we're kind of just returning control directly to the end of the function at this point, there is kind of that hidden else statement that we've gotten to line 18 because our length is long enough for us to care, and because we have a letter at the beginning and we have the letter at the end. And that highlighted text is basically where we are. The length is 118. We have a capital A in the beginning and a lowercase a in the end. So let's go back to finally our definition of our base case here. If the first, or like recursive case, pardon me, if our first and last characters match and the word obtained by removing the first and last letters of palindrome, then the initial word is a palindrome. So we have to do both those things. If the first and last characters match, somebody else please. There's so many people here today. I want to hear from more of you. If the first and last characters match, let's just write that whole comment. If the first and last characters match, and what do I say? And the resulting, this is gonna be a long comment, string obtained by removing the first and last characters is palindrome. We're good. So if the first and last characters match, we could. String compare is going to do like a whole string. We could probably sort out a string compare call that would be really nasty for this. If the first and last character match, though, doesn't require, we could probably get that to work. But it's just the first and last characters match. How do we check that? Yeah, it's just an if. I'm not saying you're wrong. Just it'd be more work than it's worth. If sentence first character sentence of 0 is equal to sentence length minus 1. That's close, but not entirely correct. What else do we have to do? Even for this instance where I said ignore case, what's one way to ignore case? They're all going to be is alpha, because if they weren't, we didn't get to this line of the code. They're both alphas. One's just a capital A, one's a lowercase a. There absolutely is, and it's called to lower. Thank you. To upper also would have worked, or you could have just written a more complex if statement, and maybe there's some trade-off there where check if it's equal to the same or check if they're off by like, the full range of letters. But that's all this function is doing anyway, right? If to lower of the first character is equal to to lower of the last character, and the resulting string, I'll add curly braces here, even though it's also just one line, but it's a complicated line. And the resulting string obtained by removing the first and last characters is a palindrome. Our string itself was a palindrome. Resulting string obtained by removing the first and last character. On line 14, we removed the first character. How did we do that? That changed the length by 1. How did we tell it to kind of shift over and ignore that first character? That plus plus, right? On line 16, we said ignore the last character or move on from the last character. And we realized we don't have to change our pointer at all, just change how far along on the string we're looking. So here we're basically doing both. Ignore the first character and now ignore the last character and call that function recursively. So what we return is going to be recursive, and it's going to be is palindrome, skipping the first, but also skipping the last. So what do we need to put for this second argument? Yep. Because we're skipping the first and skipping the last. So if the first and last characters match, and the resulting string obtained by removing the first character is a palindrome, we are good. Now, I guess we kind of got lucky based on how I wrote this function, but there is then this base case we also have to have in place here. That would have been a bug if that line 24 was not already in place, which is if this if statement was not true, meaning it was not A and A, we still have to return something. So there is also kind of an inherent else here, which is if we got to line 24, we didn't make any of these base or recursive cases, and so consequently, it was not a palindrome. Let's run it. Any predictions? How many of these are palindromes? This is clearly not a palindrome, is clearly not a palindrome. Let's just walk through. It doesn't all fit on the screen all that well, but you can kind of see, I think, in a pretty visual way, the recursion happening here. Start with the whole string. What did we do? We popped off the last character because it's not letting me select that. So let me run it from here. Popped off the last character because it wasn't alpha. Then we have an A and an A. They did match, even though one was uppercase and one was lowercase. So we called the function recursively, ignoring the first and last character. R and R, E and E. We then get to this place where it's actually space and space, but it's going to take 2 steps the way we wrote this to do so. We could have done that in 1 step, but it doesn't really matter. Then we go character by character, and it's only going to finally return whether it is a palindrome or not when we get to either a length of 1 or a length of 0, based on how we wrote this today. It's just an odd number of characters, and at least the way we wrote that, we get a T at the end. That is a palindrome. It goes all the way back up the stack. All those functions then return 1, and we do get, yes, that first string is a palindrome. Second string, this is clearly not a palindrome. Still recursive, just doesn't take very long, right? Remove the period to get the length 32. Compare capital T to lowercase e. They don't match. We hit line 24, that returns 0. We get not palindrome. Cigar, toss it in a can. It is so tragic. Looks pretty good. 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 Actually, that is also a palindrome. The example I had on the slide is it's so tragic. Okay, so we kept it as a palindrome here. And then finally, we get the final printout of our actual calling of those functions from main to get 2 of our 3 being a palindrome. Questions about this example? Friday, we're going to look at a very classic problem in computer science, the n-queens problem. So the chess team might appreciate that, although it's not strictly chess speaking. And it's one for which an iterative solution could be written, but it would take years to run. Recursive will be almost instantaneous for us. Leave things here for today. Look forward to seeing everyone here on Friday.